Pasteurization is one of the common methods used by controlling heat procedure that eliminates and kills dangerous microbes. This helps preserve food quality from its texture, taste, and color. Pasteurization is actually invented by Louis Pasteur, where the name of pasteurization coming from. However, pasteurization is initially used for wine and milk that reducing milk-borne illness and essential in public health.
However, challenges exist. Too little heat may leave microbes alive, while too much harms food quality. Energy consumption is also high. Modern solutions include thermal modeling, real-time temperature monitoring, and efficient systems like regenerative heating.
Now, let's take a closer look at how pasteurization is applied to pickled cucumbers. Firstly, the acidic brine used in pickling plays a crucial role. It helps inhibit microbial growth by lowering the pH, making it harder for harmful organisms to survive. However, acid alone is not enough. That's where pasteurization comes in. It adds an extra layer of safety by preventing the growth of mold and yeast, which can spoil the product over time. The process requires thermal precision, especially when it comes to identifying and hitting the coldest point in the product. If the coldest point does not reach the target temperature, microbes may survive. This pasteurization is typically done in a steam tunnel or with hot water, both of which help maintain the necessary temperature while minimizing damage to the product's texture and flavor.
In this study, we are using 3 egg cucumbers in 0.7 liter jars where it needs to go through 3 zones of pasteurization, which first zone is preheat with 65 degrees Celsius per 7 minutes, pasteurized with 85 degrees Celsius per 20 minutes, and lastly reaching a cooling zone with 30 degrees Celsius per 10 minutes. To guarantee the reliable processing in this pasteurization, it has an automatic conveyor, speed change, thermocouple monitoring, and temperature control system, in which actually thermocouple measuring heat at spear, center, edge, and brine. In this study, we are using 3 egg cucumbers in 0.7 liter jars where it needs to go through 3 zones of pasteurization, which first zone is preheat with 65 degrees Celsius per 7 minutes, pasteurized with 80 degrees Celsius per 20 minutes, and lastly reaching a cooling zone with 30 degrees Celsius per 10 minutes. During processing, thermocouples were inserted through the jar lid to monitor the temperature at the core and edge of the pickle, as well as the brine. And this data collected was used to confirm that the coldest point in the jar achieved and maintained the target pasteurization temperature for the required duration. The tunnel pasteurization conveyor speed and water spray temperature were adjusted based on product size and heat transfer rates to ensure uniform and efficient thermal processing.
Now, I will explain how heat is transferred in pickled cucumber pasteurization using a tunnel pasteurizer, including the product's thermal behavior and the equipment involved. As jars move through the tunnel, hot water sprays heat them by convection, heat transfer through the glass, and brine by conduction. Inside the jar, brine circulates naturally, speeding up heating. The center of the cucumber heats slowest and must stay at 85 degrees Celsius for at least 15 minutes. Pickles and brine have high specific heat, meaning they require a lot of energy to heat up. Brine transfers heat efficiently, but cucumbers and glass jars slow it down. This affects how long the product needs to stay in the tunnel. The tunnel pasteurizer moves jars through 3 zones: preheating, pasteurization, and cooling. Hot water or steam sprays jars and sensors make sure each jar stays at the right temperature. Conveyor speed is adjusted for efficiency. Combining knowledge of heat transfer, thermal properties, and equipment helps ensure food safety and preserve product quality. That's why understanding these factors is critical in food engineering.
Psychrometry is a critical aspect of thermal processing, especially in pasteurization of high moisture fruits such as pickled cucumber. This is because cucumber is a typical high level of water vegetable that more critical to preserve its texture, flavor, and overall product quality. Hence, we use psychometric trial to determine the relative humidity and dew point within the tunnel pasteurization that could affect moisture retention or leading to potential moisture loss. When the jar pass through the pasteurization tunnel, they are exposed to elevated temperature that has been mentioned before for each zone. The amount of moisture that evaporates from the tissue and the brine is depending on the chamber's humidity and dew point. Based on the result calculation, first zone has 272.12 kJ per kilogram of enthalpy and resulting a 45% relative humidity. However, for zone 2, the enthalpy for 85 degrees Celsius is 356.02 kJ per kilogram, resulting a 29% of relative humidity. And lastly, the enthalpy for 30 degrees Celsius is approximately equal to 100%. As for their dew point, the first one is 48.2 degrees Celsius, second zone is 53.1 degrees Celsius, and lastly, zone 3 has 35 degrees Celsius. Next, the principles of fluid mechanics are the main point to the effectiveness of the pasteurization process, particularly in systems that employ hot water or water steam as a heating medium. In the tunnel pasteurization, the pace and homogeneity of heat transmission are directly impacted by fluid flow characteristics including velocity, turbulence, and pressure gradients. Sufficient flow rate ensures uniform heating all of jars, promoting consistent temperature rise throughout the cucumber sphere and the surrounding brine. Moreover, the pressure drop across different sections of pasteurizer that can influence thermal efficiency. Next, an industrial application that represents the principle of thermal processing in pickled products can be observed in operation of H.J. Hinz Company, in which they utilize a continuous tunnel pasteurization system. In alignment with modern energy-saving practice, Hinz employs regenerative heat exchanger that capture heat from outgoing jars to preheat incoming products. This way use much less energy to heat up products to the right temperature for pasteurization, which can save up to 20% of total energy use.
Now let's go over some important calculations related to the pasteurization process. First one, we start by analyzing microbial reduction. Before pasteurization, the sample had 4.5 times 10 to the power of 5 CFU per gram. After pasteurization, it dropped to 1 CFU per gram. Using the log reduction formula, we calculated a log reduction of 4.65, which indicates a significant decrease in microbial load, confirming the effectiveness of the process. Next, we look at the conveyor system that moves the product through the pasteurization tunnel. The conveyor speed is 1.5 meters per minute, and the total tunnel length is 50.5 meters. By dividing the distance by the speed, we calculate the total processing time to be 33.67 minutes. This time is critical for ensuring every part of the product receives enough heat exposure. Finally, we estimate the energy usage for 3 temperature zones. First one, in the preheating zone, which is 25 degrees Celsius to 65 degrees Celsius, the energy required is around 83.68 kJ. In the pasteurization zone, which is 65 degrees Celsius to 85 degrees Celsius, it takes 41.04 kJ. And in the cooling zone, which is 85 degrees Celsius drop to 30 degrees Celsius, 110.28 kJ is needed. These calculations help us understand how much energy is consumed. The graph illustrates the heating behavior of pickled cucumbers during pasteurization by showing the core, mid-radius, and surface temperatures over time. Initially, the surface temperature rises most rapidly due to direct exposure to the 85 degrees Celsius spray water, reaching and stabilizing at approximately 80 degrees Celsius. The mid-radius temperature increases more gradually, leveling off around 79 degrees Celsius, while the core temperature representing the coldest point in the product heats up steadily and reaches approximately 78 degrees Celsius by the end of the process. This temperature gradient from surface to center confirms effective inward heat transfer and is consistent with expectation for conduction-based thermal processing. The graph indicates the changes in core temperature over time within a heating simulation. At the beginning, the temperature is 30 degrees Celsius. The temperature increases rapidly to 56 degrees Celsius at 10 minutes and then continues to increase to 70 degrees Celsius at 20 minutes. After 20 minutes, the temperature increases more slowly, reaching 76 degrees Celsius at 30 minutes and 78 degrees Celsius at 35 minutes. The graph clearly illustrates that the temperature initially increases much more rapidly but begins to taper off as time progresses. This indicates that the object heats up relatively quickly at the beginning of the simulation. This as quickly that heating intended to reach a steady temperature. Such a temperature profile also benefits analysis of heat conduction internally to an object. This pie chart represents the total energy used throughout the entire process is 230.58 kJ, which was divided into three aspects: product heating, brine heating, and system uses. Product heating used 80.2 kJ. Brine heating used 40.1 kJ. Uses were the largest aspect at 110.28 kJ. There is a large system uses pie chart section, followed by product heating, followed by brine heating. Therefore, a large portion of the energy is not used efficiently and is wasted in the system. This bar graph shows the relationship between conveyor speed and time in zone. We consider one fixed in zone distance of 50.5 meters and the values time in zone decrease as conveyor speed increase. The next graph illustrates a conveyor speed of 1 meter per minute with the time in zone of 50.5 minutes. The next conveyor speed increased to 1.5 meter per minute, resulting in the time in zone of 33.67 minutes. The final speed shown is 2 meter per minute, resulting in a time of 25.25 minutes in zone. It is evident from the bar chart that the trend declines. Therefore, increasing conveyor speeds can likely be expected to decrease exposure time to heating or process. To wrap things out, we found that the pasteurization was effective. The core temperature of the product reached 78 degrees Celsius and it stayed there for about 33.67 minutes. This helped achieve a microbial reduction of 4.65, which means most harmful microbes were successfully killed. In terms of energy use, we calculate a total of about 230.58 kilojoules and around 48.5% of the energy was used just for heating. This shows there is room to improve how we use energy. So, we should improve energy efficiency, which could save costs and be better for the environment. Second, we recommend adjusting the conveyor settings to make the process more consistent and ensure better microbial kill across all products.